it's also likely that without some support of some kind, external support of some kind, which is possible, I think there very well may be things that within our brains themselves we won't be able to comprehend.
What do you mean by support of some kind?
Well, it could take different forms. We all know, caffeine makes us more alert, more vigilant, and makes our brains work faster and better in some ways. We live in a very information-rich environment. Our brains are not, we're not evolved in such an information-rich environment. We presumably could tune our brains to accept information at a higher rate, to trust information at a higher rate without repeated presentations. All these things are part of a broader set of strategies that help us learn faster. But in terms of separating the learning and information content from sort of the deep understanding question, that becomes a little more difficult, and the external support might sort of take the form of how mathematicians use computers. It would be a bit of a bridge of some kind that we could build to external processors that allow us to work symbolically and at a higher rate than we could without such support. So I see potentially a future where human beings work together with computers to understand things as well as to remember things.
Do you envision any technology using some implants or something like that?
So implants, to do that right, one would have to have a deep understanding of the nature of information storage and processing and representation, and we don't have that yet, but we will get it. And so I think at that point, one could imagine an interface of some kind, whether physical or optical or some other form of energy or information transfer that plays a role in interface and allows that to happen.
I do think technology you've developed could be as a bridge to that.
It could be. We worked very hard on optical technologies, and it has a number of useful properties. Optical information flow is fast. Photons get scattered into the brain deeply. They come in different colors, and so you can have different channels of information flow you can play in and read out optically. It has some disadvantages. Light scattering is a big problem, fundamental limitation. We can't maintain, as you can, a sending laser through space where you can maintain its integrity over very long distances. We can't do that light in the brain due to scattering, which is one of its fundamental limitation, at least as we understand it now. So I think optical methods are useful. They won't be the full solution. We need some new ideas.
Kamran, sort of at a more fundamental level, if we are very advanced in understanding our universe, many physicists now believe that our universe is just one of many. So if this multiverse is real, do you think we can ever know anything about other universes?
Well, that's a very interesting question. As you mentioned, in string theory in particular, we think that there are other kinds of universes that should possibly exist, and we are in one of them, one particular one, but a very any host of possibilities. And now, on the other hand, in science, we have a view that if you cannot experimentally check something, that statement doesn't make sense. So if there's no way for us to actually somehow access those universes, then the question becomes metaphysical, whether they exist or not, what sense do they exist, and so on. So whether we can do it in for example, of cosmology, that our universe, for example, could emerge from another universe in some form of decay. And so, in fact, some models, there are people looking for some imprints in the cosmic microwave background of potentially that thing having happened. So those would be signatures of the would-be universes, which could be the analog of this multiverse. Whether we can actually access those now, universes, is a question we don't know yet, if there's such a way, or whether or not we can create such universes within our universe to branch off to other universes again. In principle, I don't see why we couldn't, but we're not there yet in terms of, certainly not technology, but even theoretically, we still have to understand more deeply what the theory is to see whether that can happen. But in principle, I don't see why not. In other words, that question of whether we can somehow branch out to other universes and get there may be a potential answer to Fermi's missing alien problem, and they have found a more interesting universe to be in.
So, Kamran, from the physicist standpoint, how would you summarize everything we talked about and answer the question, how much can we know?
I think probably the understanding of the word knowledge, understanding knowledge itself, what we mean by it, might have to be more refinedly defined. For example, suppose I give you a 6 billion digit number and multiply it by another 6 billion digit number, and well, can you do it? Well, we can certainly give it to a computer and do it for us, and we get the number out. And did we understand what that number came out? Well, not exactly. We know the rules in which that's happening. So it could be that what we mean by understanding and knowing might be removed from what we now think of internalizing it. So it could be a few steps down the line. Yes, we know roughly how this thing works, and within that context, we know that has been understood by something in some form, just like the way calculator multiplies numbers in some form. So that could be part of it. Or it could be that we have evolved in some way to incorporate the things that we imagine computers do, as we were just discussing, into ourselves in some way, advancing what we could understand as knowledge. So those could be part of it. But at fundamental level, we cannot beat physics. Quantum mechanics are the laws, or whatever. If that evolves, our understanding of quantum mechanics or similar things evolve, then that could put limits on us, and we wouldn't know. And we can just by analogy see that quantum mechanics is a limit of knowing, and we have to accept whatever it is, and so whatever that evolves to be, that we are left.
So it seems to me like your summary needs another summary. So let's say you would try to do it in one sentence.
There is no limit. There's no limit to knowledge except those imposed by physical laws.
Okay. Christopher, from the mathematician standpoint of view, how do you summarize your answer? How much can we know?
There is no limit to knowledge except except our imagination.
Okay.
I really think it's sort of the boundaries of our knowledge are sort of many levels removed from what we imagine right now.
And from the standpoint of biology,
I think there's no limit to our need to create workable, useful models of the universe and of our own brains.
Kim Naismith, David Spergel, and Terence Pell. Kim Naismith holds the Whitley Chair at the Department of Biochemistry at the University of Oxford, where he has done seminal work on cell division and the molecular structure of chromosomes. Welcome. David Spergel is a professor of astronomy at Princeton University and the founding director of the Center for Computational Astrophysics. He was the lead theorist of the WLMT, which got the Breakthrough Prize this year in physics, which mapped the temperature fluctuations of the early universe. And his other research ranges from matter to galaxy formation to search for extrasolar planets. And this is the last panel today, and we're going to talk about is nature simple? So, Kim, we go with you first. Explanations of the world have not always been simple, so they used to be myths and legends. Pretty sophisticated concepts, but pretty big ones. They would cover hundreds of pages. Scientific explanations seem to do a little better in terms of simplicity, but why do you think that they are simple?
Yeah, I think for me there's two reasons. The first is, I think that when explanations get very complicated, they're much harder to test, they're much harder to refute. And so you have these very complicated, the explanation, the real explanation could be complicated, but establishing whether it's right or wrong may be impossible because of its complexity. If your idea is simple enough, then it's something that is completely inconsistent with it. It's more like to say it's easier for you to realize you're wrong, and you move on. I think there's a second reason, and that is that we know that very simple processes, through iterative operations on those simple processes, can give rise to much greater complexity, emergent properties of very simple systems. And so if you see that complexity, you may feel I need a complicated explanation of it. And yet we do know that if you see this complexity, it doesn't necessarily mean that the underlying operations that are giving rise to it are themselves complex. And I think ultimately, the more simple your explanation, the more universal it will be, and the more capable it will be of generating those complexities through the simple operations of very simple processes. So I like simplicity, partly because I wasn't the brightest kid on the block at school, and I like things to be made simple enough that I can understand them.
Terence Pell, sitting in the middle, is a professor of mathematics at UCLA. He has brought new insights to a wide range of mathematical fields, including harmonic analysis, combinatorics, partial differential equations, and analytic number theory. And somehow, over time, we just started to use more and more mathematics to explain the world around us. So why do you think it's happening, and why mathematics is so efficient in describing our world?
Well, the universe does seem to have a simple basis, but the primitive objects of the theory are very far removed from our human experience. So we can't use anymore sort of our regular human intuition to understand particles or quantum waves or fields. And so what's left when you don't have direct human experience is mathematics. I mean, it's a perfect language for dealing with things that you can only see indirectly. I take Kim's point that simple explanations are preferred, but I have to say it's still a miracle that we have one. I mean, the default should be complexity. So you can show mathematically, like if you take a random string, say 1 million digits, normally this has no pattern to it. You need about what, if you want to describe this string, you need about 1 million characters to describe the string. There are a small number of complicated strings that can be generated from simple rules, but these are really hard. Einstein once said that the most incomprehensible thing about the universe is my help. Sorry. Yeah, Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. And I don't think we really have a good explanation yet. Okay. Sorry, Yuri. Yeah, so the most incomprehensible thing about the universe is that it is comprehensible. I don't think we really have a good explanation for that.
Maybe we just hold it.
Okay.
Now, yes, this is something that physicists have been struggling for a while. You know why? And you are quoting Wigner saying the most incomprehensible thing about the universe that it is comprehensible. So, what would be your answer to this? So, why, Terence? What would be your guess?
I don't know. Actually, well, maybe there is one possible explanation, which so there's another mathematical phenomenon which is universality. That if you have a very complicated law of physics at the microscale, sometimes when you look at what emerges, sometimes it gets more complicated, but sometimes it gets simpler. So that the most famous example is famous examples are laws of thermodynamics. So both classical and quantum systems are very different at the microscale. They obey the same laws of thermodynamics at the microscale. So maybe the laws of physics are really just a mess below the Planck scale, but some universal law kicks in, and above a certain scale, things become simple, and then they become complicated again. But,
So, David, sort of continuing this conversation of simplicity and complexity, how to explain the relative simplicity of theories explaining the universe at very small scales and very large scales, and it seems like this amazing complexity emerging somewhere in the middle.
Yeah, to follow on the previous comments, the really shocking thing about the universe is at the small scales, things are simple. Just remind people that you look out to all this complex biology. It's made of atoms. There's only 100 or so atoms. Atoms are made of neutrons and protons and electrons, so like 3 types of stuff make up that. When you look at neutrons and protons, they're made up of quarks. Everything that happens in nature can be described by 4 basic forces. It gets down to what we think ultimately will be unified in 1 force. So on the microscopic scale, things are incredibly simple. To me, the shocking thing when we look out in space and look at the microwave background, it's incredibly uniform. The properties of the fluctuations are incredibly simple. Everything that we could see in the fluctuations can be described by a handful of numbers. So on both its smallest scale and its largest scale, the universe is simple. In some ways, that may be linked. When we think about going back in time towards the Big Bang, as we get to earlier and earlier in the history of the universe gets hotter and hotter. The physics of the small, we think, may determine the properties of the large. And one of the things that we've been learning, and string theory colleagues have been learning from studying the properties of string theory of gravity, is duality. That there's a real link between the properties of the small and the properties of the large. So perhaps the fact that one is simple makes it inevitable that the large scale stuff is simple. So then given that it's simple on the small scales and simple on the large scales, why does it end up being so complex and interesting in between? And I think, for me, the best answer there is once you have interactions, once you have nonlinearity, once lots of stuff works together, complexity seems to emerge. And even that complexity itself often has universal laws.
Is gravity really the explanation, basically?
I think gravity is, the simplicity of gravity and this underlying simplicity of the universe on the smallest scales is what's motivating things like string theory is just remarkable. Now, why is it there? Why is it so simple? We don't know, but everything we have learned seems to point towards things being simpler and simpler the deeper and deeper we go. Now, simpler requires mathematics. That's not the mathematics of addition and multiplication. We have to learn mathematics from our colleagues, but ultimately, it's just amazing to me that our brains are capable of contemplating and understanding things on both the smallest and largest scales.
And Terence, does it really apply to mathematics itself that it gets, in a way, simple in terms of unified in a certain way, or there's just a lot of complex, relatively unrelated fields emerging?
Well, the trend over time has been towards more and more unification in mathematics. The analogy that many mathematicians use, I don't know who it's first due to, possibly Andrew Wiles, but that's one guess, is that initially mathematics felt like a whole bunch of isolated mountaintops separated by this huge mist below which we couldn't see. And so geometry is here, and algebra is here, and number theory is there. And then slowly over time, fields got connected. So Descartes famously unified algebra and geometry with his Cartesian coordinate system. And over time, more and more connections were made, and you start seeing these valleys appear as the mist slowly goes down. And then eventually we start seeing interesting forests and just much more interesting things at the root, which we wouldn't have expected. Very abstract concepts which we didn't initially know about. Once we knew about them, they are simpler, and they explain the peaks a lot more. And I think mathematics is a bit further along the unification process than physics and certainly life sciences. For example, physicists are still searching for the universal laws of physics, the grand unified theory. They've been unified for quite a while, they're not quite there yet. Mathematicians, we have found our laws of mathematics. We basically have a final form since the days of Hilbert about a century ago. So we have the rules of mathematics. We haven't explored the consequences of those rules. So I mean, that's the beginning. But yes, certainly the trend is towards unification. Also in mathematics, we also see the same trend that at extremes, when you set a parameter to be very small or very large, often the theory becomes simpler, easy to explain. There's maybe just only one dominant effect and everything else is perturbative. It's in the messy middle when there's many competing effects that you want to analyze. This is often where things are difficult.
Kim, what about biology? Do you think there are some sort of universal laws and principles that would apply to the universe anywhere?
Yes, I think, that relates back to our last discussion. At the moment, we can only see and study life on this planet, and it all looks as if it's descended from a common ancestor. Maybe we'll find independent offshoots if we go and dig in deeper in different places. Maybe we won't. If we found it elsewhere and it didn't look like anything else, it was clearly of an independent origin, we weren't directly related, then it would allow us to see what's common. If it had evolved separately and it ended up in the same place. And that we could then begin to formulate a sort of universal laws of biology. But in order to do that, we've got to find life somewhere else.
Obviously, that would be great. Terry, just one more question for you. Some proofs that have been emerging recently are so complex that sometimes there is not even consensus among mathematicians as to whether they're correct. There are probably a couple of examples like that. Is that always a temporary stage before someone else will simplify things, or they can just continue to be very complicated? In other words, would it be proper to assume that over time, if somebody was able to prove something in a very complicated way, then eventually there will be a simple, more elegant proof?
I mean, this is certainly the trend. Often what happens, it's not necessarily shrinking the size of a single proof, but putting if you have many difficult results, if you can put them inside a single theory, which itself may be somewhat difficult to understand, but once you understand that theory, if all these difficult results are just simple consequences of that theory, that is a great step for advance, even if it means that if you, the actual length of a proof of any given result hasn't increased, it hasn't decreased, because you have to understand first this theory before you understand any one of its conclusions. There are still big mathematical results that have not been simplified substantially. One of the most famous is something called the classification of finite supergroups. So these are describing all the finite symmetries that you can get in the world, and they use results of what are called the simple groups, which can actually get quite complicated. There's a list. There's like 4 families, and then a list of sporadic groups. So this is a known theorem. It's called the enormous theorem because there's no one place where you can find the proof. It's split up over hundreds of papers, maybe 10,000 pages total. And actually, there have been some minor issues in some of these papers that have to be corrected. There is an effort underway to make a second generation proof, which is a little bit simpler, but it will still be a 1,000-page proof. Hopefully, I mean, there is progress, and it is slowly getting simplified. One major chunk of it, called the Van-Thompson theorem, recently got computer verified, for instance. So at least on that one major part of the proof, it's completely correct. We have a computer verification. But there should still be a more conceptual proof. It shouldn't just. It's hard to believe that this rather basic result of mathematics is so irreducibly complicated that it has to take thousands of pages to prove.
So you are yourself at the forefront of this seemingly new emerging trend where mathematics becomes more a collective effort. Many mathematicians involved in proving some conjecture, plus involving some computers. Is that sort of the way that mathematics will work in the future? Combination of relatively large groups of people and machines?
It's moving in that direction. So we certainly rely a lot more on machines. The type of questions we consider now are much more interdisciplinary. It used to be that we would, every different field, like we're stuck on these mountaintops, the geometers would only work on geometry questions, the algebras would only work on algebra questions. But nowadays, to make progress, you have to use ideas from different fields, both within mathematics and outside mathematics, and so you need to talk to more and more people. And also with the internet, it's much easier to collaborate. It used to be you had to be in the same university, or at least physically be present, visit somebody for a long period of time. Now you can do it mostly online. So mathematics has become a lot more collaborative. I've been involved in a few projects that involve maybe up to 100 people online. Not nearly as big as the physics and science collaborations yet, but we're moving in that direction. Yeah, so that's going to be more and more that was mine.
Interesting. David, could the multiverse that we mentioned a couple of times today explain why our universe appears to be the way it is and being explained by more or less simple rules?
Well, I'm going to say something which I probably shouldn't say in Palo Alto. I don't think the multiverse is a testable and interesting scientific hypothesis. I think it doesn't explain anything. The way the multiverse tends to be used is together with the anthropic principle. The idea that the universe is the way it is because that's the way we get to live. I find the multiverse solutions to these problems somewhat like that. You ask me, why am I wearing a black shirt today? And I answer, I'm wearing a black shirt. And my answer would be, you wouldn't have asked the question if I wasn't wearing a black shirt. That's not a satisfactory answer. If the multiverse, the way we have advanced in science is by falsifiability, by developing hypotheses, testing them, that's what we do, experiment, and ruling things out. Ideas that are not testable. It's interesting metaphysics. It's interesting branches of, perhaps interesting for philosophers. What has driven 400 years of scientific progress is the fact that ideas can be wrong. And the multiverse, I think, is kind of the last refuge of cowards. Well, that's why it's great to have tenure.
So that wouldn't be a good way to end our panels today. I want to thank all the panelists, of course, including this one.
Thank you so much. What I'm trying to do today is give you a brief introduction. This thing can happen over the next 10 years if we pay attention to the health of our cells. Every one of our bodies is made up of some 10 to the 13 cells. And what makes cells work are the marvelous machines, molecular machines that are encoded in our proteins. So proteins, usually if you Google protein, you just end up with food websites and nutritional substances. But the reason why we eat proteins is to take them apart and build proteins in our cells that then can carry out these marvelous functions. So proteins function as enzymes. They convert metabolites and food substances. They are the motors that exert mechanical forces to move things about and to move inside the cell and the cells themselves. Structural proteins function as mechanical devices to give cells their rigidity. Then we have receptors and signaling proteins that receive information and allow cells to communicate with one another to have an organized organism. Gene regulatory proteins tell the genome which gene to express when and where in an organism in a cell-specific fashion, and so on and so on. Every one of our cells makes about 1 million to 1.5 million proteins every hour. So it's a huge process going on in the cell. We've learned a lot about protein synthesis. The ribosome translates the copy of the genome, the messenger RNA, and it translates it into a linear sequence sequence of amino acids, and once these amino acids are polymerized to one another in their specific sequence, they are an unfolded chain, and this is cartoon shows us the length of this chain that then has to be folded up into a three-dimensional shape so it can carry out this function. And this is the degree of compaction drawn approximately to scale here. The reason for this compaction and the folding is that now in the folded protein you can bring amino acids together that can carry out certain chemistry and that provide what's called the active site with which proteins now can fulfill these different functions. What we've learned over the last years by many different groups is that this process of folding up a protein is very complicated. It's in most cases assisted by cellular machinery. There are folding intermediates that the protein undergoes before it reaches the finally folded state. Proteins are then degraded, so there's control how much of a protein is around, and worn-out proteins get tagged to be degraded. But these processes also can go wrong, and you can end up with unfolding of folded proteins. They can state into unproductive misfolded states, from which they can be either rescued or they can be shunted into degradative pathways. And finally, proteins can aggregate into either amorphous aggregates, just think of a hard-boiled egg, or structured proteins that then can be toxic aggregates and are associated with many of the neurodegenerative diseases. And from there, they can be shunted into degradative pathways. This is a very active field.